Grid computing. Unit 4. Data management in grid computing refers to the processes and technologies used to manage and store large amounts of data across distributed resources in a grid environment. Grid computing presents unique challenges for data management, including the need to manage data across multiple sites, handle complex access and security requirements, and ensure reliable and efficient data transfer. One key technology used in data management in grid computing is grid FTP, a protocol designed for high-speed data transfer across a grid. Grid FTP allows for reliable and efficient transfer of large files across distributed resources, even in the face of network latency and errors. Another important technology used in data management and grid computing is grid-enabled storage systems, which allow for efficient management and sharing of large data sets across a grid. These systems are designed to provide scalable, reliable, and secure storage of data, and typically use advanced technologies such as distributed file systems, storage area networks, SANs, and parallel file systems to achieve high performance and reliability. Metadata management is also a critical component of data management in grid computing. Metadata refers to data about data, such as file names, locations, and access rights. Effective metadata management is necessary for locating, accessing, and managing large data sets in a grid environment. Several tools and frameworks have been developed for data management in grid computing, including the Storage Resource Broker, SRB, and the Grid File Transfer Protocol, Grid FTP. These tools provide a range of features and capabilities for managing and accessing data across distributed resources in a grid environment. In summary, data management is a critical component of grid computing and requires specialized technologies and processes to ensure reliable, efficient, and secure storage and transfer of large data sets across distributed resources. Grid-enabled storage systems, metadata management tools, and high-speed data transfer protocols such as Grid FTP are key components of data management in grid computing. Structured data refers to data that is organized into a specific format with a well-defined schema or data model. Structured data can be categorized into several types based on its format and origin. Relational data. This is the most common type of structured data and is typically stored in relational databases. Relational data is organized into tables, with each table containing a set of rows and columns. The schema for relational data is defined using SQL, structured query language, which allows users to query, update, and manipulate the data. XML data, Extensible Markup Language, XML, is a markup language used for storing and transporting structured data. XML data is organized into a tree-like structure, with each node representing an element or attribute. The schema for XML data is defined using Document Type Definitions, DTDs, or XML schema. JSO data, JSO, JavaScript Object Notation, is a lightweight data interchange format that is widely used for web applications. JSO data is organized into key-value pairs, with each key representing a data element and the value representing the data. JSO data is easy to read and write, and can be easily parsed by many programming languages. RDF data, Resource Description Framework, RDF, is a standard for describing resources on the web. RDF data is organized into tuples, with each tuple representing a subject-predicate-object relationship. RDF data is used for representing metadata and data about resources on the web. Structured data can originate from various sources, including databases. Most structured data is generated and stored in databases, including relational databases, NoSQL databases, and object-oriented databases. Web services. Structured data can be generated by web services such as REST and SOAP. Log files. Log files from various sources such as web servers, network devices, and operating systems often contain structured data. Sensor networks. Many IoT devices and sensor networks generate structured data in real time. In summary, structured data can be categorized into several types, including relational, XML, JSO, and RDF data. Structured data can originate from various sources, including databases, web services, log files, and sensor networks. Data management in grid computing can pose several challenges due to the large-scale nature of grid systems and the distributed nature of data. Some of the key challenges in data management for grid computing include data storage. Storing large amounts of data in a distributed environment can be challenging. Data must be distributed across multiple nodes in the grid, which can lead to issues with data consistency and access control. Data transfer. Moving data between nodes in the grid can be time-consuming and resource-intensive. Large data sets must be transferred efficiently and reliably to ensure that they can be accessed by users. Data replication. Replicating data across multiple nodes in the grid can help to ensure availability and reduce data transfer times, but it can also create issues with data consistency and synchronization. Data security. Protecting data in a distributed environment can be challenging. Data must be secured both during transfer and storage to prevent unauthorized access. Data access. Providing users with access to data across a distributed environment can be challenging. Data must be cataloged and indexed to ensure that it can be found and accessed easily. Data integration. Combining data from multiple sources can be challenging due to differences in data formats and schemas. Data must be integrated and normalized to ensure that it can be used effectively. Data processing. Processing large amounts of data in a distributed environment can be challenging. Data processing tasks must be divided into smaller subtasks that can be executed in parallel across multiple nodes in the grid. In summary, data management in grid computing can pose several challenges due to the distributed nature of data and the large-scale nature of grid systems. These challenges include data storage, transfer, replication, security, access, integration, and processing. Addressing these challenges is critical to ensuring that data can be managed effectively and used to support scientific research and other grid computing applications. Database integration with grid computing involves making databases available as grid resources to provide distributed data management capabilities. By integrating databases with grid computing, organizations can take advantage of the scalability and processing power of the grid to manage large volumes of data in a distributed environment. There are several approaches to integrating databases with grid computing, including grid-enabled databases. Grid-enabled databases are databases that have been modified to run in a grid environment. These databases can be accessed and managed by grid middleware, making them available as grid resources. Database virtualization. Database virtualization involves creating a virtualized database environment that can be distributed across multiple nodes in a grid. This approach can be used to provide distributed data management capabilities while minimizing the need for complex database replication and synchronization. Middleware database connectors. Middleware database connectors are middleware components that allow grid applications to access and manipulate data in a database. These connectors can be used to provide seamless access to database resources from within grid applications. Data grids. A data grid is a specific type of grid that focuses on providing distributed data management capabilities. Data grids are designed to enable the sharing, management, and processing of large data sets across multiple nodes in the grid. In addition to these approaches, there are also several tools and platforms that can be used to facilitate database integration with grid computing, such as the Globus Toolkit, which provides a range of services and tools for integrating databases with grid computing. Overall, integrating databases with grid computing can provide significant benefits in terms of scalability, processing power, and distributed data management capabilities. This can be particularly important in scientific research and other applications that require the management of large volumes of data. Collective Data Management Services, CDMS, are a set of architectural approaches for managing data in distributed systems, such as grid computing. These approaches focus on providing scalable and reliable data management capabilities by leveraging the collective resources of the system. There are several CDMS approaches, including replication-based CDMS. This approach involves replicating data across multiple nodes in the distributed system. This provides high availability and fault tolerance, as data can be accessed from multiple nodes even if some of the nodes fail. However, this approach can also result in increased data management overhead, as data needs to be kept consistent across all nodes. Caching-based CDMS. This approach involves caching frequently accessed data on local nodes in the distributed system. This can reduce the latency of data access and improve performance, but it may also lead to data inconsistency if updates are not properly propagated to other nodes. Distributed Query Processing-based CDMS. This approach involves distributing query processing across multiple nodes in the distributed system. This can improve the scalability of the system by allowing queries to be processed in parallel, but it may also result in increased network traffic and communication overhead. Publish-subscribe-based CDMS. This approach involves publishing data to a centralized service, which then distributes the data to subscribers. This can be an efficient way to disseminate data to a large number of subscribers, but it may also result in increased latency and network traffic. Peer-to-peer-based CDMS. This approach involves distributing data across a peer-to-peer network. This can provide scalability and fault tolerance, as data can be accessed from multiple nodes, but it can also result in increased network traffic and communication overhead. Overall, the choice of CDMS approach depends on the specific requirements and characteristics of the distributed system. Different approaches may be more suitable for different types of data and different types of applications. By leveraging the collective resources of the system, CDMS approaches can provide scalable and reliable data management capabilities in distributed systems such as grid computing. Federation services are a set of architectural approaches that enable data and resource sharing across different administrative domains in distributed systems, such as grid computing. These approaches provide a mechanism for connecting different systems and allowing them to work together, even if they are owned and managed by different organizations or individuals. There are several different federation service approaches, including Identity federation. This approach involves allowing users to use their credentials from one system to access resources in another system. This can be achieved through standards such as Security Assertion Markup Language, SAM, or OpenID Connect. Resource federation. This approach involves allowing resources to be shared across multiple systems. This can be achieved through standards such as Open Grid Services Architecture, OGSA, or the Open Grid Services Infrastructure, OGSI. Service federation. This approach involves allowing services to be shared across multiple systems. This can be achieved through standards such as the Web Services Interoperability (WSI) framework or the Web Services Resource Framework (WSRF). Data federation. This approach involves allowing data to be shared across multiple systems. This can be achieved through standards such as the Open Archives Initiative Protocol for Metadata Harvesting, OAI-PMH, or the Common Data Model, CDM. Workflow federation. This approach involves allowing workflows to be shared across multiple systems. This can be achieved through standards such as the Workflow Management Coalition, WFMC, or the Open Grid Services Architecture Data Access and Integration, OGSADI, framework. Overall, federation services provide a flexible and scalable way to connect different systems and enable them to work together. By supporting different types of federation services, distributed systems can be integrated to create a larger and more powerful system that can meet the needs of a wide range of applications and users. Middleware is an essential component of grid computing as it provides a layer of abstraction between the underlying hardware and software resources and the applications that use them. Middleware is responsible for managing and coordinating the resources, data, and services that are distributed across the grid, making it easier for users to access and utilize these resources. Some of the key reasons why middleware is important for grid computing are: resource management. Middleware provides a unified view of the resources available on the grid, making it easier for users to manage and allocate resources as needed. It provides a set of tools and services for scheduling, monitoring, and managing resources, which can help optimize resource utilization and reduce costs. Data management. Middleware provides a unified view of data on the grid, making it easier for users to access and manage data. It provides a set of tools and services for data discovery, transfer, and management, which can help optimize data access and reduce the time and effort required to manage data. Security. Middleware provides a set of security services and tools for managing authentication, authorization, and encryption. This helps ensure that grid resources and data are protected from unauthorized access and helps ensure that users can trust the security of the grid environment. Interoperability. Middleware provides a set of standards and protocols that enable different grid components to work together seamlessly. This helps ensure that users can access and use resources from different grids and enables the development of cross-domain applications. Overall, middleware is important for grid computing as it provides a layer of abstraction and a set of services and tools that help manage and coordinate the resources, data, and services that are distributed across the grid. It provides a unified view of the grid environment, making it easier for users to access and utilize the resources they need to perform their work. There are several types of middleware used in grid computing, including grid middleware. This is a middleware specifically designed for grid computing. Examples of grid middleware include Globus, Toolkit, Unicore, and GGSIPU. Distributed middleware. This middleware is designed to provide a consistent interface for distributed computing resources, including grids, clusters, and cloud computing environments. Examples of distributed middleware include Apache Hadoop, Apache Spark, and Kubernetes. Messaging middleware. This middleware provides a messaging infrastructure for communication between distributed applications. Examples of messaging middleware include ActiveMQ, RabbitMQ, and Apache Kafka. Enterprise middleware. This middleware is designed for use in enterprise environments and provides services such as transaction processing, security, and database access. Examples of enterprise middleware include IBM WebSphere, Oracle WebLogic, and Red Hat JBoss. Web middleware. This middleware provides services for building and deploying web-based applications, such as web servers, web frameworks, and application servers. Examples of web middleware include Apache HTTP Server, Nginx, and Apache Tomcat. Operating system middleware. This middleware provides services that bridge the gap between the operating system and applications, such as process management, memory management, and file system access. Examples of operating system middleware include Microsoft.NET, POSIX, and Corba. Overall, the type of middleware used in grid computing will depend on the specific requirements of the application and the environment in which it is deployed. Grid middleware is specifically designed for the unique requirements of grid computing, but other types of middleware may also be used depending on the specific needs of the application. There are several middleware solutions available for grid computing, including both open source and commercial offerings. Here are some examples of globally available grid middleware. Globus Toolkit. This is one of the most widely used open source grid middleware solutions. It provides a set of services and tools for managing and accessing distributed computing resources. Unicore. This is a European middleware solution that provides a grid computing framework for managing distributed resources. It includes a set of services for job submission, data management, and security. GGSIPU. This is a middleware solution developed by the European Grid Infrastructure (EGI) project. It provides a set of services and tools for managing and accessing distributed computing resources. ARC. This is a middleware solution developed by the Nordugrid Collaboration, which is a collaboration of Nordic and Baltic countries. It provides a set of services for job submission, data management, and security. Open Science Grid (OSG). This is a distributed computing infrastructure that provides access to grid resources in the United States. It is built on top of the Globus Toolkit and provides a set of services for managing and accessing distributed computing resources. GridGain. This is a commercial middleware solution that provides a distributed computing platform for managing and accessing distributed resources. It includes a set of services for job submission, data management, and security. Data Synapse Grid Server. This is a commercial middleware solution that provides a distributed computing platform for managing and accessing distributed resources. It includes a set of services for job submission, data management, and security. Overall, there are many different middleware solutions available for grid computing, each with its own strengths and weaknesses. The choice of middleware will depend on the specific needs of the user, as well as the requirements of the application and the available resources. The Globus Toolkit is an open-source middleware solution for building and using grids. It provides a set of services and tools for managing and accessing distributed computing resources. The Globus Toolkit was developed by a team of researchers at the University of Chicago and the Argonne National Laboratory. The Globus Toolkit includes several core components, including Grid FTP. This is a high-performance file transfer service that is optimized for wide-area networks. It allows users to transfer large files over long distances and across different types of networks. Grid Security Infrastructure (GSI). This is a set of security services that provides authentication, authorization, and encryption for grid resources. GSI is based on Public Key Infrastructure (PKI) and provides a secure environment for grid computing. Grid Resource Allocation Management (GRAM). This is a service that allows users to submit and manage jobs on remote grid resources. GRAM provides a standard interface for job submission and monitoring and allows users to access resources from different grid environments. Grid Computing Globus Toolkit Replica Location Service (RLS). This is a service that allows users to discover and locate data replicas in a grid environment. RLS provides a standard interface for data location and management and helps users to optimize data access and transfer in a distributed environment. The Globus Toolkit also includes several other services and tools, such as the Grid Security Certificate Authority (CA), which is responsible for managing digital certificates, and the Grid Development Tools (GDT), which provides a set of tools for building and testing grid applications. Overall, the Globus Toolkit provides a comprehensive set of services and tools for building and using grids. It has been widely adopted by the scientific community and is used in a variety of scientific and research applications.